Hello, this video is going to be about system identification and why I prefer the Levenberg-Marquardt or the lmfit module of Python to do my system identification. So before you can see some Python code, which is my code for running the lmfit. And the system I'm going to identify has 15 parameters, and I can show you the final result here. And you can't really tell it's nonlinear by this graph, but you can see that a swept sine wave was used to do the system identification. There are a little bit more than 3 seconds worth of data, so there's 3,040 points taken at 1 millisecond intervals. And the green line is the control output, which is the swept sine wave. The cyan line is the actual positions that was recorded, and then the estimated positions, or my model, generated the red dotted line. And you can see that the Levenberg-Marquardt system did very well at estimating the valve response. So this plot shows the nonlinearity. It takes about 20% to get past the null. In other words, you don't get any flow until you get past about 20%. And then you can see the flow increases, but it's not linear. And again, this is a nonlinear valve, so this is what I expected. But at first, I didn't expect it to be this bad, so I'm going to show you about some of the steps that I took. So, but first I want to talk about this program, and you can see that what I'm doing here is reading the file, and I got a time array, the control output, and the actual recorded positions. And then I have to use an interpolation function because I'm trying to do a deadband estimation, and the deadband might not be an integer value of milliseconds, so I have to interpolate between the milliseconds. So that's why I have this interpolate routine. You can see that I have 15 parameters, and this is the ratio between the extend and retract directions. This is part of the differential equation. It's 2 times zeta omega. We have A2, which is omega squared, or natural frequency. We have the deadband and offset, and then 10 gain segments. And the 10 gain segments compensate for the nonlinearity. And then I'm measuring the time, and then printing out the results. So what happens, this is printing routine, which isn't that important, the data routine. This is the T1, P2. That means I've got an integrating system with 2 poles, and I use ODE to calculate or to do the differential equations. And this part takes care of the 10 gain segments. You can see I've got a gain segment from 0 to 5, 5 to 10, 10 to 15, 20, 30, 40, 50 to 60, 80, and 100. And what's different about the Levenberg-Marquardt system and the other systems that just use the minimize is that the Levenberg-Marquardt system uses a dictionary to pass params. So you can actually have a lot of attributes with each parameter, whereas with the other systems, you kind of have to add the limits separately. The bounds is what they call it. So what happens with the Levenberg-Marquardt system is that you have 15 parameters. So think of that as 15 dimensions. And I know that's hard to think about. So let's just think about 2 dimensions. You have 2 parameters, and you can go north-south for parameter 1 and east-west for parameter 2. And what you would do is you take a step in each direction and try to determine which way is downhill, then start going in that direction. Well, with 15 parameters, what you end up doing is taking 15 steps and then moving in that direction. And Levenberg-Marquardt is very good at estimating how far it needs to move in the downhill direction. So you can see that the next estimation has a much lower sum of error squared. Now, the sum of error squared is actually the sum of all the errors between my model and the actual position. So there's 3,040 points. So the sum of errors squared can be very big at first when the estimate or the initial guess is not very good. But you can see that the sum of errors squared is reduced by quite a bit. The thing that's different, another thing that's different about the Levenberg-Marquardt system is that it actually returns a um, what it is an array of all the differences. It doesn't return the sum of errors squared. It returns an array of the differences. So that part is much different. So let's go back to here. And so what's happening is you can see that after a few steps, the sum of errors squared drops by quite a bit. And finally, we get down to where the sum of errors squared is very small. And the sum of errors squared is what I used for just seeing the progress. Again, the Levenberg-Marquardt system uses an array of differences. And then you can see the results here. And then these are the estimated parameters. And these are used to estimate the response on plot that you saw it originally. But the big thing is the root mean square is 0.004, and this is fractions of inches. So root mean square, 4 thousandths of an inch is the estimated error. So uh, again, the Levenberg-Marquardt system works pretty quickly, but originally what I did to start with is a linear fit, and I'll show you that. And you can see the response is not that good. And we know that the linear fit's not going to work. You can see that it just tries to estimate just the curve with linear segments. And the sum of errors squared, or the root mean square, finally is not that good. And you can see that the sum of errors squared is not as low as what it was before. So I knew that the linear curve was not going to be what I wanted. The next thing I tried was a fifth order. And the reason why I tried a fifth order is because the valve has a positive flow when you give it a positive output, and then a negative flow when you have a negative output. So it needs to have an odd function. So what I used for my function is x and c times x. That's the bias or the offset, and then I have a c3 times x cubed, and then a c5 times x to the fifth power. And you can see that this estimate is much better, but it's got problems. If I go here, you can see that it does okay, but once I get past 80% control output, I don't have any data, and so the fifth order curve just kind of does what it wants to do, and this is not accurate. So what I knew I needed to do is somehow extend the estimations out beyond 80%. And the fifth order curve was not going to do it. I could have tried a seventh and a ninth, but I decided to try a linear segments instead, because I knew if I made them close enough, it would be good enough. So you can see the sum of errors squared is much better than or the root mean squared is much better than what we got for the linear segments, but not near as good as the Levenberg-Marquardt with the 10 segment estimations. And this was a 0.004 for uh, the non or the 10 segment version. So the Levenberg-Marquardt system works fairly quickly, and the option is to not use the Levenberg-Marquardt and to use uh, the built-in optimizer that comes with scipy. And I'm going to open that up now. Oh, I want let's see. I want to open up the. Okay, now This is a little bit different. You can see that you pass the parameters that you're trying to estimate in an array instead of in a dictionary. You need a separate bounds array, and then you have to make the call to the um, minimize routine. And the minimize, you can see that I've tried many different minimize routines here. And the one that works best is this lbfgs-b version. And what it requires is the sum of errors squared, not array of residuals or differences. So then what happens, you get the result, and then you can print that out. The big thing is, again, it uses the sum of errors squared, and where the BFGS system might come in handy or better than the Levenberg-Marquardt is that you can have a more complex uh, estimation routine or evaluation routine that might take in several variables. So you can have a more complex cost function. So then what happens, you generate a sum of errors squared instead of an array of residuals, and then you try to minimize the sum of errors squared. So up here, it's basically the same code. I'm generating a sum of errors squared, and that's what I'm returning here instead of residuals. This is basically doing the same thing, only I'm using arrays instead of dictionaries. So what are the results? Well, the results are these. Let's start with here. And you can see that the estimations are pretty good and almost as good as what the Levenberg-Marquardt optimization routine returned. This looks almost identical. And oops. And you can see that this is the root mean squared is 0.004 instead of 0.005. But what's significant here is the elapsed time took, well, it looks like 100 minutes, more than 100 minutes. Whereas let's go back to the results on the Levenberg-Marquardt, you can see that this is only 15 minutes. So this is about 15 times faster than the BFGS. So I don't know what magic that they pulled in the Levenberg-Marquardt module, but it functions much faster than the basic modules, the minimized module that comes with the scipy. Excuse me. So here you can see that again I have the same 15 parameters with the same limits. It's basically calling the same code for display. And again, the only difference is that I have to use, well, this is the Levenberg-Marquardt routine. Let's get back to the, there. Let's get back to here. We're using an array. And now I'm going to talk about the other methods that are commented out. Again, I've spent a few hours trying this, and one of my favorite minimize routines is the Nelder-Mead, and that's this function here. And I tried all the different options that might make it better. And the problem with the Nelder-Mead is it works fine if you only have about 5 or 6 parameters, but with 15 parameters, it doesn't work very well. What I like about the Nelder-Mead is it doesn't require finding a Jacobian or any derivatives. So it's a derivative-free system, and what ends up happening is that if you happen to have 15 points, like in this example, you start out estimating 16 different locations, and then what you do is an evaluation at each one of these 16 locations, and then it takes the worst location and it moves it closer to a better location. Then it reevaluates all the locations and it finds the worst one and it'll move the worst one to a better location. And as it's moving it to a better location, what happens is that you might be starting out with 16 dimensions, and they kind of converge. And what happens is that it will eventually collapse down to a point where it's not going to move very fast, and it takes forever to converge when you have 15 parameters. Another methods that I like is Powell's method. Powell's method, again, works very well if you don't have a lot of parameters. One of the reasons why I like Powell's is it doesn't depend upon derivatives. It just figures out two directions to move, and then it moves until it finds a minimum, and then it makes another line. And the problem that I run into with the 15 parameters is that eventually it gets close, but all these different lines that it generates don't go through the minimum, so it starts going back and forth, and it never converges. BFGS works well, but not quite as well as the LFBF, BFGS-B. And then congruent gradient basically suffers from the same problem as the Powell's method. It basically is always trying to find a slope that's, I guess you could say perpendicular or normal. I'm not, it's kind of hard to explain. From the last direction that it went, and the problem is these directions are not the steepest downhill, and what happens is it never converges because it starts going back and forth around the optimal position. Now, one of the things that I've tried playing with is to use one of these methods to get close, and then use the Levenberg-Marquardt. But the Levenberg-Marquardt converges so much faster than the rest of these that I can get by with just the Levenberg-Marquardt by itself. However, I have another video where I'm doing a system identification on a temperature system, and what I use is the Powell's method to get close, and then I use the BFGS, I mean the Nelder-Mead to finally get to the final position. Uh, Again, if you only have 5 parameters, Nelder-Mead works just fine. What I like about the Nelder-Mead and the Powell, again, is it doesn't require derivatives, and if you're working with real data instead of some sort of equation, it's nice to have a derivative-free method of getting to the minimum point. And somehow the Levenberg-Marquardt system manages to get around that problem. So that's why I like the Levenberg-Marquardt, because it doesn't seem to be too affected by the noise, and yet the fact that it can estimate the downhill direction makes it converge faster than either of these two. If you have any questions, ask. That's all I have for this video, and stay tuned for another one.